action that we wrote last time. We finally wrote the Nambu-Goto action. So that was given minus T0 over C integral d tau from some initial tau to some final tau, d sigma from 0 to some sigma 1 square root of x dot x prime squared minus x dot squared x prime squared. And dot and primes refer to derivatives with respect to tau and derivatives with respect to sigma. And they have a mu index over here. So this formula is a key formula and basically defines everything we need to know about the theory. We've put this tension here, and the units work out correctly. The units of x's are length. The units of an action must be equal to the units of h bar. We're keeping every unit in there, so it's ml squared over t. And we can look at the units of this thing. Now, it's a nice fact, perhaps related to reparameterization and variance as well, that the units of tau and sigma do not matter. They could be length, time, or whatever, but you have a d tau here, and you have two d taus here, and two d taus there, so they cancel. Then you have a d sigma, and you have 1 over d sigma here because of this prime derivative squared, also 1 over d sigma squared here. So the sigma units and the tau units don't matter. And that's interesting and nice. So sigma and tau units drop out. And x has units of length. So you have an x, an x squared, an x to the fourth. So this whole thing, the units of s, are the units of t naught over the units of c times length squared. So it just remains to be checked that the units of t naught over c are m over t, because the action must have those units, and you have the L squared in both sides. The units of t naught over c, t naught is a force, so it's a mass times an acceleration. So it's a units of a velocity divided by t. That's t naught. And then the c is a units of velocity, 2 units of velocity. So t naught over c has units of m over t. So the units are correct. T naught over c has units of m over t, and you have L squared. They work out. So with the units right, you realize that this has the interpretation of a force, and we'll see that that is the tension of the string. No, it's not obvious at all from this, just writing this action, that that's supposed to be the tension of the string. Maybe the tension of the string is 3 times that, or some other number. We'll see why that is the tension of the string. The other thing that is perhaps useful to realize here is that we can write this action as an area element if we use the induced metric in space-time. In the same way that we were talking about the induced metrics in space for surfaces, induced metric in space-time, you remember, ds squared minus ds squared was eta mu nu dx mu dx nu. That's our metric in the space-time where the string is propagating. So to get the induced metric, you think of these x's as the x's of the string. So you have eta mu nu dx mu d psi I times d psi I, dx nu, d psi j, and this is the induced metric eta ij of psi on the string. As you measure things on the surface of this string that is moving in space-time, it's a two-dimensional surface. It's a funny surface. We learned last time the most important property of this surface, the thing that really makes strings, is that this surface at any point has at least one space-like vector and at least one time-like vector corresponding to the propagation in the future. So this is the two-dimensional induced metric. And you can see that this is this Nambu-Goto action is minus T naught over C integral d tau d sigma square root of this term is gamma xi's. Remember, the xi i's are tau and sigma. So this is xi 1, 2 squared, the gamma 1, 2 squared, minus gamma 1, 1, gamma 2, 2. So it's minus T naught over C integral d tau d sigma square root of minus the determinant of gamma. That's minus the determinant of gamma. So a little like in general relativity that you write Einstein's actions or things like that, square root of minus g d for x and something. Here you just have the square root of the metric, the relevant metric, the metric induced on the surface that the string is moving on, and the differentials. So it's an area, but it's a space-time area. So before we now try to understand the physics behind this, which is going to occupy us today, all of this lecture, and probably a little bit of next time the classical physics about this action. Let's stop and see if we have any questions or any. Take a minute break to pause and reconsider these things. Yes. Dan.
Looking at the string as a sheet in space-time, as it evolves, does the minimal surface principle apply to it? So would it naturally take the configuration that minimizes the space-time surface area?
Right. So the good question. That anticipates a discussion problem you're going to have this afternoon. This is a very important issue that shows up everywhere in physics. You know, there's this issue that they say, well, you try to minimize the action, and then somebody tells you, watch out, you're trying to make the action stationary. That's all you know. So for sure, this area is being made stationary. The question of whether it's being made a maximum or a minimum can vary, or it might be a saddle point. In general, it's just the stationary point of the functional. So this is something that you can learn in differential geometry. Like, what is a geodesic? Well, you might say, oh, it's the shortest curve between 2 points. Sometimes. What is a geodesic? In fact, is a path that makes the length stationary. Suppose you have a cylinder and you have 2 points. What is the geodesic? Well, you can say, go here. But maybe it might be that it's shorter to go like this and come back from the other side. and that could be shorter, or you may go several times. The shortest, the thing that is stationarity is the real definition of things. So this will not necessarily be the minimal area, but it will be the stationary area. And the problem you will do this afternoon is a simple harmonic oscillator, and you will try to imagine at one time it's here, at another time the harmonic oscillator has moved, it's here. Does the solution minimize the action or not? And you will find that sometimes it minimizes it if the two times are close by. But after a while, for solutions that join things that are happening at times larger than half the period of the oscillator or something like that, it need not be a minimization. It might be something else. So another example, if you have a sphere, you can take 2 points and you say, oh, the geodesic is the thing that joins them, a simple thing. And then you can draw a maximal circle joining these 2 points. But this other curve is also stationary. And it's not the shortest one. Any fluctuations of it can make it smaller as you just go around it. So this is a minimal length geodesic, and this is a geodesic of stationary length. So the same thing will happen here. It's a very nice thing. I actually learned that from Alan Guth, that example of the oscillator that you will work out this afternoon. It's a very neat example. It clarifies this issue of when the action is supposed to be minimized, maximized. In fact, when you vary a field, you're fluctuating in many directions. You know, when you vary, for example, this geodesic here, you have many parameters that characterize the fluctuation. So the parameter space is infinite dimensional. So you have maybe, one deformation is this one deformation is this one, another deformation. There are infinitely many deformations. Some are minima, and some are saddle points, for example. So the typical critical point will be a saddle. It will be a minimum for some directions, but a maximum for some other directions. It's a neat story. But enough of a digression. Let's go on now with this thing. I like the middle one first. So how about the variation of this action? Well, this action is d tau d sigma minus t naught over c. And it's a Lagrangian density that depends on x dot and x prime. And this is the notation we used last time to vary the non-relativistic strength. And then we define px to be, don't copy this yet, dl with respect to y prime. Well, we'll do here, say with respect to x dot. And since we're doing time, we'll call it tau, p tau. In fact, I will call it p tau mu, because you have a mu index in here. And I'll have p mu sigma, because we differentiate with respect to the prime derivatives, which are sigma derivatives. So I'll put the sigma here and a mu there. So there's two types of things. Whenever you want to vary x, you will say, oh, I want to vary x, so I must differentiate L with respect to x dot and then vary x dot. That's why this quantity is useful, and this is why that other quantity is useful. So I will, maybe I should do it like this. P mu sigma is dl dx mu prime. Now, can those be calculated? Yeah. This L, remember, is square root of x dot x prime squared minus x dot squared x prime squared. So I can take the derivative with respect to x dot mu. Well, square root, so 1/2, 1 over that thing, times the derivative of this with respect to x dot. You have a 2, you have this factor, and then you get a differential with respect to x dot, so you get an x prime. So the 2's cancel. Well, there's more things there, but I'll just write it, and I put the dots, because whenever you have a square root inside, there is this thing. And this one would be x dot dot x prime mu. That's from this term. When you differentiate this term, you're differentiating again, you get the 2 that cancels the 1/2 of the square root. And then you get an x dot left over, and an x prime squared. So here must be minus x prime squared x mu dot. This is messy. This you can write as well. I won't bother. And that's why we don't want to use this formula unless we need to. We want to just work with these objects. Their interpretation will become clearer tomorrow, in fact, because there's more to be said about them. But for the time being, I just say, OK, let's do the variation of the action. And what do we get? Well, I'll rely on your remembering or having notes of how we varied the other one, because it's exactly the same. The only difference is that primes were x derivatives and dots were time derivatives. Now prime are sigma derivatives and dot are tau derivatives. So we get this kind of thing, p mu sigma delta x mu between sigma 1 and 0. And I'll just say a few more words about it, but there's minus c over t naught here. That's delta s. Oh, no. What am I talking about? Well, I confused you. I'm sorry. L is everything that you integrate. So I was being silly. Here is minus t naught over c. That's L. Minus t naught over c times all these things. So there's no t naught and c or anything. This is all just clean and nice. The tau, the sigma, delta x mu, dp mu tau d tau, plus dp mu sigma d sigma. Okay, let's just make sure we know what's happening here. Remember, we vary these things and vary x dot, and then we integrated by parts because this was the tau derivative of delta x, and then the tau derivatives were integrated. The prime derivatives of delta x, they were integrated. And the time ones that involve time infinity and minus infinity, we could forget about them. We'd never deal with them. Nevertheless, there's the problems at the endpoints of the strings. And remember, we had a p times a delta x that we had to consider. And it's just the same thing here between sigma 1 and 0. And here is the equation of motion. The equation of motion is dp mu tau d tau plus dp mu sigma d sigma equals 0. How bad is that equation of motion? It's awful. It's just incredibly complicated. Look, suppose you had to differentiate this with respect to sigma again. It's very messy, several lines. Differentiate with respect to tau, several lines, that's equals 0. That's the equation of motion. It's so difficult that we would have 0 chance of solving it ever. That's another thing that is interesting in a sense. Had you tried to invent a relativistic string by inventing an equation of motion, you would have to have suddenly come up with the idea that d tau of this thing plus d sigma of that thing should be 0, and essentially impossible. The action is very simple and innocent looking, and the equation of motion is a tremendous mess. So our goal today will be to begin to simplify this, and what do we have at our disposal? You know, string theory at this level is general relativity in action. In general relativity, coordinate transformations is a nice abstract thing. Well, our life here depends on being able to choose clever enough tau and sigma coordinates such that this equation simplifies. You have the choice of choosing tau and sigma however you like. And clever, physically motivated choices will simplify this dramatically. And you will understand what's really going on. If you don't make those choices, the situation is absolutely impossible. Now, the thing we have here, too much. Let's look at boundary conditions, which is quite important. So what do we need to happen? Remember, we called sigma 0 or sigma 1, this set of values, sigma star. So what do we need to happen? We need that P, this term be 0, this first term. And how do we achieve that? Well, there's two kinds of things. Let's look at that term, and this is tau sigma star delta x mu at tau sigma star. Apparently, this must be 0 at the endpoints. And we saw last time that when we had this equal to 0 was a Neumann boundary condition that was free. And when you say the variation, you cannot do arbitrary variations, means that you fix the string at that endpoint. So that's it. That's Dirichlet. Now, this does look maybe like Dirichlet, although this one doesn't look anything like Neumann, because P sigma is that very complicated stuff there. But it's free, because you don't put anything here, so presumably that's free. And we should trust that since we don't put any constraint on delta x, this is the free thing, free boundary condition. But I want to go here through more things. I want to say, look, at the end of the day, you're supposed to do the thing at sigma 1 minus the one at 0. But I didn't bother to do that. I told you before that you don't want to cancel the variation at sigma 1 with the one at 0. These are far away points, nothing to do with each other. I want to tell you something more. You don't really want to cancel this thing by summing over mu. You don't want that the boundary condition in the x direction confabulates with the one in the z and in the w and all these directions to solve it. This is something that it's a funny statement, but for the time being, I will do that, and I will show you that in general you can do that you should think of each one of this as separate, the different mu's. The fact that you have a sum, and you can say, look, there's just one boundary condition. The sum of all that is 0. That's not quite true. This is, you have enough freedom to impose conditions in all kinds of ways, and therefore there are many conditions that you can impose here, and you should try to do the best. So in fact, what I claim is that you must have P 0 sigma tau sigma star delta x0 tau sigma star equals 0, and pi sigma tau sigma star delta xi tau sigma star equals 0 for I not summed. These boundary conditions are the key of understanding what a D-brane is, which is going to show up in a couple of minutes. So you see, I'm going to impose more conditions, which really means that I'm making the physics richer and richer. By understanding, I can impose more and more conditions on the variations. So apparently, as we said last time, you can choose this one to 0 or this one to 0, this to 0 or this to 0. Or can we? There is a slight complication here. Let's look at the first one. Well, this to 0, sure, we could put that to 0. How about delta x0? Can I say that delta x0 is constant? That I'm not going to allow x0 to change? That doesn't make sense. You know, this particle, you can say, or this string has an endpoint. And the endpoint is like a particle, and the particle, whether it does anything, it has to move in time. So its x0 position cannot be held constant. It's totally unphysical to hold it 0. So this cannot be 0. Delta x0, x0 cannot be fixed. It must evolve. As tau changes, the time on that endpoint of the string must change. And therefore, this cannot be 0. So we must always have P0 sigma of tau sigma star equals 0. That must be imposed, and that's the only thing you can do. Then you can do P I sigma of tau sigma star equals 0, or you could say delta xi of tau sigma star equals 0, which you take it to mean that xi of tau sigma star is a constant, or that dxi d tau of tau sigma star is equal to 0. It's a fixed number. It won't change. So either this, or this. Now, I'm done with these blackbirds. So this would be a Dirichlet boundary condition. So here we go. This is what really defines whether you have a D-brane or not. So let's draw a D-brane, our first D-brane, and state what are the boundary conditions. So here is a plane, and you have a D-brane, which is just a hyperplane. And I'll put the hyperplane in the x2, x1 direction. And the x3 is normal to the hyperplane. So what does it mean to have a D-brane? What is the definition of a D-brane? A D-brane means that the open strings have endpoints and must stay within this hyperplane. So if this sheet would be a D-brane, all open strings are expected to have the endpoints on this sheet. This is the equivalent in when you had a string fixed at 2 points here. You would say you have a heavy D-brane here and a heavy D-brane, and the endpoints must be there. it's surprising how long it took physicists to discover D-branes. Now it looks crazy, but can you imagine the non-Mugoto action was studied for 20 years before anybody thought of a D-brane? It's force of habit, a little fact that boundary conditions scare us, a little subtle, and what do you do? And moreover, you know, people thought this is absolutely crazy. You have a string, the D-brane would break Lorentz invariance. This D-brane is translational invariant along itself, but it's not breaks symmetry in the x direction. So breaking Lorentz invariance out of the question. Why? You know, people just would never consider anything like D-branes. It's sort of funny. And moreover, once they said, well, we can break Lorentz invariance by forcing the string to be there, but what is there? There's only strings. But this is the funny thing. The string theory is almost asking you or telling you that other things can exist. And it took until basically the 90s for people to suddenly wake up to the discovery of this thing. Now, here we say that this is fixed. And you can ask, well, if this thing is a D-brane, why is it fixed if it's really a physical object? Well, what we'll learn is that the mass or the energy density of this D-brane is very, very high in normal circumstances. So it's very heavy compared to the little strings. So it almost doesn't move them. But if you want to treat them correctly, they move and they do things. So that is a D-brane for you. Now, what did people used to do before D-branes? They had open strings moving just freely in space. No idea that there's anything. So if I would ask you, what does it mean now in the light of D-branes to have an open string that moves all over space? Suppose you come to this room and you imagine your shoelace is an open string and it's just moving all over. What does it mean in terms of D-branes? My question is a little ambiguous, but life is a bit ambiguous. Yes?
Whole space is one D-brane?
Yeah, that's what it would mean, that the D-brane is filling this room. Because the open strings endpoints must stay on the D-brane. So if they're freely to move, must be because the D-brane is space filling. This would be called a D2 brane because it has two spatial dimensions. Now, before we take to the issue that string theory has 10 dimensions or whatever, you can think of D3 branes. If you had a D3 brane, it would fill 3 spatial dimensions, would fill this room. The strings would seem to be free. These were the only strings that were known until 89 or something like that. Open strings were supposed to be free. And because they were supposed to be free, nobody thought there is a D-brane filling the space. Moreover, that D-brane had energy density. And nobody knew of that energy density. But now we know, and actually it has to do with tachyons and things like that. It's a very lovely story of how things were discovered quite accidentally. So the other objection is that the D-branes break Lorentz invariance. But if you have higher dimensions, suppose you have 10 dimensions, you can imagine the D-brane filling all your 3 spatial dimensions, and no Lorentz invariance is broken, and filling some number of the extra dimensions, breaking the Lorentz symmetry in the compact extra dimensions. That's okay, that's unobservable. 4-dimensional Lorentz invariance survives. So it has become the most useful tool of string phenomenology, D-branes. It's a whole subject, basically. Yes?
But didn't you just say that it didn't break Lorentz invariance in principle because it has a finite mass and so it actually moves?
it would move, but suppose you have a D-brane, suppose there is a D-brane here, big D-brane going through, a D2 brane going through the middle of your galaxy. The universe is not rotational invariance anymore, it's not translational invariant, it doesn't look homogeneous. You break a big D-brane, breaks spontaneously Lorentz invariance. It makes the universe, the idea of Minkowski space and Lorentz invariance is that the universe looks at large scales, totally homogeneous, isotropic, translational invariant, rotational invariant, all those good things. But if there would exist a big D-brane over there, it's not symmetric anymore. Okay, so what are the boundary conditions when you try to write mathematically this D-brane? You would say, look, I have to put boundary conditions. All the boundary conditions must be specified. The one that always is there, P0 sigma tau sigma star would be 0. That's always there. Now for the motion along the x1 direction, I need to say something. Is it free or is it constrained? Along the x1 direction, the open string can move freely in the x1 direction because it's a direction on the D-brane. So it's a free direction. So x1 is free at endpoints. So you must have P sigma 1 of tau sigma star equals 0. How about x2? It's also free. It's also direction on the D-brane. P2 sigma tau sigma star equals 0. And x3, however, the point cannot move out in x3. It's stuck. x3 is fixed. x3 is 0 in this picture. So here you would put x3 of tau sigma star equals 0. And those are your equations that define this D-brane. And with those equations, you can calculate any motion of an open string attached to a D-brane. So let's begin trying to understand the physics of these equations a little more. And in order to do that, we're going to start working out the idea of parameterization invariance. So reparameterization invariant, coordinate invariance, as I said, in general relativity is a lovely abstract thing. Here you have to deal with it concretely. You're going to try to do it. So what does it mean choosing a parameterization? Here is your world, x0, x1, x2. And then there is tau and sigma. Is that right? There's sigma here, and here is tau. Is the parameter space, a grid. And what is choosing a parameterization is finding how to map this grid, how to put the grid here, how to draw the lines of constant tau somehow, and how to draw the lines of constant sigma. So I give you a surface, and you teach me how to draw those lines. That's the name of the game. So I'm going to begin to draw some lines. I'm going to do the easy ones now. I'm going to teach you how to draw the lines of constant tau in a useful way, in a physical way. And this is called the static gauge, a name that is absolutely confusing. Static gauge. But the intuition is simple. You basically are here. Here is x0. And you decide, look, let's take a picture of the string in this Lorentz frame at some time t0. And therefore, taking a picture of the string at that time t0 is like drawing a hyperplane here. And you will see a string here. And then under the hyperplane, there's this thing. So at some time, you look at your string. At 10:56, you take a picture of the string and you say, oh, it's 10:56. So I'll say this is the line of tau equal 10:56. So basically, you're going to put tau equal to the time. That's the idea. Putting time equal to tau or tau equal to time. You have to try to think about it, what it really means. It really means that at some time you take a picture of the string, and that string that you see, as you see in the surface, is the string at tau equal time. So we'll simply say that we'll set tau equal to t. Now, t is what we call x0. So basically, x0 of tau and sigma is now going to be just tau. Now, there's a factor of c in there, because we'll think of tau as units of time. So I'll just say c tau. So this is the so-called static gauge. With this, I fix tau. I've learned how to fix tau using the time. It is the most natural thing you could do. Tau is time. Now, what happens when you do that? Well, a few things simplify, like dx mu d sigma would be dx0 d sigma times dx vector. We split the mu indices in 0 and vectors, d sigma. And that's dx0 d sigma is 0. 0 dx d sigma. And dx mu d tau would be dx0 d tau. And dx vector d tau. And dx0 d tau is c. And dx d tau, this I think bothers you. It's very important. I'll just write it dx, not d tau, dt, because t and tau is the same thing. This is ct. So these things become very understandable objects, as we will see now. So one more thing then, we can go and calculate our first example of a string. Let's take a string stretched from x1 equals 0 to x1 equals a. And therefore, this string, is a relativistic string, has x1 of t and sigma. I'll write what it is, but x2 of t and sigma is equal to x3 of t and sigma. And if you have more dimensions, they're all 0. This string is stretched from x1, from the x-axis, from 0 to a. That's the end of that string. Now, what is x1 of t and sigma? I'm going to call this sigma equals 0, the beginning of the string, and this will be sigma equals sigma 1. x1 of t and sigma, well, it's certainly, we're having it stretch and staying there, so it's time independent. It can only depend on sigma. You could say, well, what function of sigma? How do I draw the various sigmas here? Well, should we take linear? Should we take What should we do? Well, we trust reparametrization invariance, or we don't trust reparametrization invariance, the question is. If we trust it, we can take anything, and the answer should not depend on how we parameterize, so maybe it's a good check. So let's take it arbitrary. It's some function of sigma, such that f of 0 is equal to 0, f of a, of sigma 1, I'll take sigma equals sigma 1 equal a here. Just unit of length there. So sigma f of a, no, I'm sorry. I'll leave it sigma 1. F of sigma 1, I'll leave it very arbitrary. It's going to be a. And how is this function supposed to be? Well, the only thing I need is that for sigma, here is sigma 1, and here is a. The only thing that I need is that it monotonically grows, because it cannot stop growing, because then you don't parameterize well. So it's some arbitrary function that does that. OK, so what do we have here? We have, let's look at the coordinates x mu. Well, the first one is ct. The second one is f of sigma, is x1, x0, x1, and all the others are 0. What is x dot mu? Well, you're differentiating with respect to tau, but tau is t, so this is c, 0, and 0. What is x prime? Well, there's no sigma dependence here, so it's 0. Here is f prime of sigma, its derivative, and 0. So what is the x dot x prime, which is an ingredient in the Nambu-Goto action? The dot product of this thing, 0. What is x dot squared? That's equal to minus c squared. What is x prime squared is equal to f prime squared. So what is the Nambu-Goto action? S is equal to minus t0 over c integral d tau integral d sigma from 0 to sigma 1 square root. We have the action there still. X dot x prime is 0 minus x dot squared minus c squared. X prime squared f prime squared. So look how nice. Minus t naught over c d tau d sigma from 0 to sigma 1. The c has cancelled. The c goes out and cancels. And f prime is df d sigma. And this integral is a total derivative. It will give you the value of f at sigma 1 and the value of f at 0. The function did not matter. Reparametrization invariance worked. So here we get minus t naught d tau, dt, in fact. I don't need to call it tau anymore. It's t. dt f at sigma 1 minus f at 0. And therefore, it's the integral of dt of minus t naught times a. We've finished our calculation. But there's an enormous amount of stuff to learn from that calculation. And the thing to learn from that is first, reparametrization invariance worked out. Now, what is the action? Action in general is the integral over time of t minus v. If there's no kinetic energy, is the integral over time of the minus the potential energy. This thing definitely has no kinetic thing. at least intuitively, is absolutely clear. And therefore, what we have in there is the potential energy of that string. And that potential energy is T naught A. T naught is a force, and A is a distance. It's like the energy of that string is the tension times its length. It is as if you had grabbed that string of 0 length and stretched it to length A with a constant tension force of T naught. That's the work done. That's the rest energy of that string. That string sort of doesn't have mass. It has rest energy because you've created it, and the tension is confirmed to have the interpretation of tension. The energy you need to create that string of length A is the tension times the distance. You want 2A, tensions times 2A. The tension doesn't change however long the string is. So you buy a relativistic string, you hook it here, and you just, each time you want to jump the rope with your string, you just begin to stretch it, make it any length you want, and then you can start doing anything you want with it. It actually transforms work to rest mass. It's a machine that transforms work to rest mass. If you just do the work, start stretching the relativistic string, then once it's totally stretched, you've stored in this string that much energy, T naught A. That's sort of the rest mass of this object. So tension times distance is the rest energy of a piece of string. And the string seems to have a constant tension. That's already very different from a normal string, and that starts to tell you that the string is very interesting. Yes?
If the string is massless, would you be able to stretch it, which is in the end acceleration?
If it's what?
So if the string is massless,
yes, which
is the gated thing, then would you be even able to stretch it?
I think you should. You know, it's this is a very hypothetical discussion because obviously I don't know how you grab a relativistic string. I've never seen one real made or anything close to it. But the end result is you can imagine holding it to a D-brain perhaps and then moving the D-brain, for example, and stretching the string. That definitely should be possible. And then, you know, you compute the work and you realize that. So at the end of it, you have a string like that, and somehow it stores energy T naught A. That's the rest energy of this string. So it has a rest, you could say it has a rest mass of this divided by c squared, a mass per unit, the total mass, P0 over c squared. And what is the mass per unit length would be mu divided by A is T naught over c squared. So the mass per unit length of the relativistic string is given by the tension. It's not an independent parameter. I have to move on to describe one more concept so that you can solve your homework this afternoon. Not homework, the discussion section. And you know, there's really lots of physics here, beautiful, simple physics, and that's why it's fun to see. It's nothing terribly sophisticated mathematically, but the ideas are really quite surprising. So here's another idea that is fairly surprising that we've been talking about, that you cannot tell really how the string moves, what points, how a point moves. So if you have a string here, and you have a point P at some time t, and you have the same string here at some time t plus dt, and this is a picture of the string in space. In space, this is not a world line of a string. When I show you a string, it has to be a picture of the string in space, because in space-time, the string is just a more abstract, complicated object, traces a surface. So here is the string, and here's the string a little later. We don't know, because of reparameterization invariance, where this point goes. Because if this is a point sigma sigma hat, well, you can choose sigma hat to be anything here. So where did it go? Well, we know it cannot move faster than light. And say if light could go this far in this time, it could have gone anywhere here up to here. We don't know. And therefore, it's hard to define the velocity of this point. You say the velocity of this point would be dx dt. But dx dt is calculated keeping sigma constant. But precisely, we don't know if sigma is constant. So this may not be the velocity. So how can you define a velocity that is independent of parameterization? You can define one, and it's called the transverse velocity. You take the point P, and here is the string, and draw the plane where the string is perpendicular to this plane at that point. So if the string is here, and you are interested in this point, put a plane perpendicular to the string. Then a little later, the string will intersect the plane somewhere else. So the assumption is that a little later, of course, it will intersect it somewhere else. And the transverse velocity is the velocity assuming that the point moved transversely to itself. It's a well-defined velocity. It's not the velocity, but it's the best thing to the velocity. It makes physical sense. It's perpendicular to itself, and it's a transverse velocity. So how do you calculate this? The way to do it is to, this is called the V-perp, is a transverse velocity. It's a very fundamental concept. It's this idea that you assume that the point moves transverse perpendicular to the string at that point. So how do we do this? In order to do this, we'll think of a parameter. We'll trade sigma for a parameter s, which is going to be a length along the string. Along sigma. So S, don't confuse it with proper time, with anything. I'm sorry, we ran out of letters. It's going to be a length along the string. So if you take a little piece of string, dx, a piece of string, along the string, and when I now say along the string, that means at constant time, which is the same thing as constant tau. It's along the string, then ds is equal to the length of this piece. It's a length parameter, so ds is equal to dx like that. Since dx is along the string, this is dx d sigma times d sigma. And by using chain rule, this is dx with respect to s times ds with respect to sigma times d sigma. So this is certainly dx ds times ds. So you convince yourself that dx ds is a unit vector. Because ds is equal to this, so this length is unity. This is a nice thing. Now you have a unit vector. Now, oops, this is the real one. Now, more things. Almost done, but a couple more minutes. So how do we write a formula for this transverse velocity? I'm going to draw a little picture here. Here are lines of time, t plus dt, t a little later, and here are sigma lines. sigma, sigma plus d sigma, and things like that. Now, where is the vector dx times dt? This is the picture of the string in space. Picture of string in space, not space-time. We drop space-time. So any vector here is a vector with an arrow. This is how the string surface looks as it moves in space. Imagine the string is like the object that leaves a weight after it moves. So it leaves this surface. This is how it looks in space. Now, dx dt means how x changes. Take a point as you change t without changing sigma. So that's a vector tangent to the sigma line. This is, I erase those words here, dx dt. But dx, the perpendicular velocity, is the velocity assuming that this point P moves perpendicular to the string at this time. This is the string at this time, the string at a later time. So dx, the perpendicular velocity is this one, is v perp, is the component of this perpendicular to the string. And here you have the vector, the unit vector dx ds. Look, all these vectors, the naive velocity, the perpendicular velocity to the string, and the vector along the string that is a unit vector. So what is this thing? Is this vector minus the component along the string. So the perpendicular velocity is the original velocity minus the component of the original velocity along this, the dot product, times that unit vector. So dx dt, dx ds, yes, times dx ds. This is a dot product. When you want to find the component of a vector along perpendicular to some direction, you use a unit vector. This is what we do. We subtract the piece along that. That's v perp. Now, this is the only sort of natural velocity defined independent of parameterization. You don't need the parameterization to have this velocity, because in order to have this velocity, you look at the string at any time, draw a plane perpendicular, and assume it moved there. So if all these things about reparameterization invariance are true, the action should be possible to express in terms of that. Now you have v perp, you have the static gauge, and you can compute x dot, x prime, all these things. So this is an exercise left to you, but this whole square root of the Nambu-Goto action, it's in the book, so you could read it, or you could just challenge yourself to do it. This whole square root is nothing but c ds d sigma times 1 minus the square root of v perp squared over c squared. It does work out. Only the perpendicular velocity comes out of this. This is like half a page calculation. So it means that the Nambu-Goto action is what? Minus t naught over c, but the c will cancel. dt ds square root of 1 minus v perp squared over c squared. And then you can recall the action of a point particle, S of a point particle, was integral over T of a Lagrangian of a point particle, and the Lagrangian of a point particle was minus mc squared square root of 1 minus v squared over c squared. And this is the rest energy. Lagrangian is energy units. Rest energy times the relativistic factor. Look at that. You could have invented this whole thing if you thought clearly. this is integral dt minus t naught ds times 1 minus v perp squared over c squared. Remember, t naught ds is that energy in a little piece of string, the rest energy of a little piece of string, times the relativistic factor, assuming the transverse velocity. The whole thing has been reduced to that. So when you try to solve the mechanics of a string, the problem that you will do this afternoon, you will be given a round string. And you will ask, you let it go. What does the round string do? Well, the round string will start collapsing and oscillating and doing funny things. This Lagrangian is the easiest one. You start with Nambu-Goto, you're never going to get through it. But now we've gotten the physics right. Finally, this string Lagrangian of a relativistic string has become something that it's even analogous to the particle in another way, and the rest energy is all from tension. All right, we'll see you tomorrow.